Hi guys, I'm always being asked to make a perfect answer version of my biology video for both chemistry and physics, so I'm going to try and do a chemistry version today. So I'm going to go through what I consider to be some fairly difficult questions and show you my approach to answering them. So we're going to start with this question first of all. The reaction used to make polyethylene can be represented by this equation. Describe the differences between the reactant and product in this reaction, and in your answer you should refer to carbon chain length, type of bond and state of matter. So it's worth 3 marks, so I need to refer to carbon chain length, type of bond and state of matter, and I know if I don't refer to all 3 of these things then I can't possibly get full marks. So let's first of all look at our monomer. Well, this is ethene and this is polyethylene or polythene, which is a plastic. So starting with the carbon chain length, remember that polyethylene, poly means many, so it's going to have a much longer carbon chain length when compared with ethene, which only has 2 carbons. So I'm going to make that comment first of all. And make sure you write a full comparison. Next up, we need to refer to the type of bond. And as we can see here, we have a double bond in ethene and a single bond in polythene. So ethene has double carbon bonds, whereas polyethylene has single carbon bonds. And then lastly, state of matter, we need to refer to whether they're solid, liquids or gases. Ethene is a gas, whereas polyethylene is a solid. So as with all science, you're not really looking to write amazing prose or anything. Just make sure you write a full comparison and that will make sure you get all 3 marks. The second question I'm looking at is the diagram showing a kettle of boiling water. As the water vapour cools, it turns into droplets of liquid water. The change of state when water vapour changes into liquid water is described as condensation, so that's B. Describe what happens when water vapour cools to form liquid water. Your answer should include the change in energy, arrangement and movement of particles. And actually, handily, they've written that out for us, so we don't have too much to do. So hopefully you know that a gas has lots more kinetic energy when compared with liquid. So the particles are widely spaced, they have lots of kinetic energy and they have low forces between them. In a liquid they're far closer together, they have less kinetic energy and stronger forces between them. So let's make a comparison when we go from water vapour to liquid water. Water vapour particles lose kinetic energy to become liquid water. Change in arrangement, clearly the water particles are closer together in liquid. And lastly, change in movement. Well, the particles in liquid will obviously move more slowly. Next up, I'm going to show you how to approach an organic chemistry question. So the table shows the displayed formula of 4 hydrocarbons, W, X, Y and Z. And before I even get going on the questions below, I like to do the first thing, which is to write the molecular formula of each of these compounds. And so I'm counting the carbons in W, there's 3 of them. I count the number of hydrogens, there's 8 of them, C3H8. I remember that monkeys eat peanut butter to help me name it. It contains 3 carbons, so peanuts, so that is propane. Let's do the same here now for X. We have 4 carbons, 10 hydrogens. Monkeys eat peanut butter, so that's butane. Now to work out this one, we again have C4H10. It's going to be harder to name. Let's count the longest chain. It's prop, as there's 3. And there's a methyl group, so it's 2-methyl propane because of that CH3 group. And then lastly, looking at Z, well, we have C3H6 and this is propene. And this should make it nice and straightforward to answer the questions. So give the name of hydrocarbon W. Straight away I can see that it is called propane. Give the molecular formula for hydrocarbon X. Again, I've already done that, so that's C4H10. Which of the hydrocarbons belong to the same homologous series of compounds? Remember, these are compounds that have the same functional group, the same general formula, and I can see that we have 3 alkanes here, which are W, X and Y. Give the empirical formula of hydrocarbon Z. So looking at C3H6, I need to cancel that down. I can divide both by 3, so that becomes CH2. Z is an unsaturated hydrocarbon. Explain what is meant by the term unsaturated hydrocarbon. So let's make sure we name both parts of here. So unsaturated means that it contains C double bond C, so that's carbon, carbon double bonds. Hydrocarbon, it's a substance containing hydrogen and carbon atoms only. You must say the word only here to get the mark. The substitution reaction between W and bromine is similar to the reaction between methane and bromine. And remember, W is propane, C3H8. Suggest the displayed formula for a possible product of the reaction between W and bromine. So I'm going to write my equation down here to help me work this out. So we have propane, which is saturated, it's an alkane. I'm adding bromine to it, and remember it's diatomic, and it's a substitution reaction, which means that only one of those bromine atoms is going to add itself. So the product will look something like this, and you'll have HBr left over. So in terms of answering the question, suggest the displayed formula, so I need to show the bonds, and I need to show that it's this product here. And remember to count up your bonds and make sure that each carbon only forms 4 bonds and each hydrogen forms 1. State the condition required for this reaction to take place. That requires you to remember that it is UV light. And there was the other product, because I realised the camera probably wasn't pointing. Question 5. A student investigates the pigments found in some vegetables and fruit. She obtains some coloured vegetable and fruit extracts from carrots, tomatoes and sweet potatoes. She places a spot of each extract on chromatography paper along with spots of 3 pigments of beta-carotene, chlorophyll and lycopene. Her teacher provides a solvent containing volatile, flammable organic compounds for the experiment. The diagram shows the apparatus at the start of the experiment. So make sure you do read every single word. Explain why it's important for the solvent level to be below the spot, and that's just to prevent the spots mixing. State 2 potential problems that are prevented by fitting the tank with a lid. That's a fairly strange question for chromatography, so we need to look back at the description to see if there's anything hidden in there, and there is. It says that it's a solvent which is volatile and flammable. So why might we want to fit a lid? Well, it could be to prevent the evaporation of the solvent, because remember, volatile substances evaporate easily. And flammable, well, we don't want to start a fire, so we want to prevent the risk of a fire really by placing a lid on it. The diagram shows the chromatogram at the end of the experiment. Here's the key to the vegetable and fruit extracts and pigments. Which 3 of the statements A, B, C, D and E are supported by the chromatogram? Okay, I can tell this is going to be quite difficult. So I'm actually going to write what each of these codes means, even though the key's right there, it will help me out. So that's the carrots, these are the tomatoes, these are the sweet potatoes, here's the beta carotene, here's the chlorophyll, and here's the lycopene. So we're trying to work out which of the statements A, B, C, D and E are supported by the chromatogram. So chlorophyll is not present in carrots, sweet potatoes or tomatoes. So I'm looking up chlorophyll here, and I'm saying it's not present in carrots, tomatoes and sweet potatoes. No, there's no line across level with the chlorophyll, so that's true. Beta carotene is present in carrots but not present in tomatoes. So here's the beta carotene. It's present in carrots, yes it's here, but not present in tomatoes. No, it's here, so that's not true. Both beta carotene and lycopene are present in sweet potatoes. So here's lycopene, and I'm having a look to see if it's in sweet potatoes. Yes it is. And then I'm looking at beta carotene now, which is up here, and yes it's also present, so that's correct. Lycopene is present in tomatoes but not present in carrots. So yeah, it's present in tomatoes, but it's also here, so it is present in carrots. So that's, I'm not going to put a cross there. Both carrots and tomatoes contain a pigment other than beta-carotene, chlorophyll and lycopene. So looking at carrots and tomatoes, yeah, there's this extra dot and this extra dot which doesn't correspond to any of the 3 pigments. So yeah, that is also correct. So I hope you can see that by labelling your exam paper you can actually help yourself answer pretty tricky questions. I now want to touch on a covalent bonding diagram. So a molecule of carbon dioxide contains double covalent bonds. That is key that you notice that. Complete the diagram using dots and crosses to show the arrangement of the outer electrons in a molecule of carbon dioxide. So handily they've already shown the arrangements of the atoms, so I'm just going to fill in. This is going to be really wonky. No! Needs to be more circular than this, guys. Should have made my middle circle bigger. So I've added my circles to represent the outer shell of electrons, and I know it contains double covalent bonds, so the easiest thing for me to do here is to show those double covalent bonds. And I know that each carbon atom has 4 electrons in its outer shell because it's in group 4. Oxygen is in group 6, which means it has 6 electrons in its outer shell. So we've already got 2 here, 3, 4, 5, 6. Let's keep it nice and symmetrical and do the same on this side. And then you just need to add up and make sure they both have full outer shells. Yes, they both have 8 in their outer shells, so they are fine. Indium is a metal in group 3 of the periodic table. Describe the structure and bonding in indium. Don't worry because you've never heard of the element indium. Crucially, it's a metal. So because of that, remember it has positive metal ions surrounded by a sea of delocalized electrons. So don't let the question confuse you. I'm just going to say here that it's made up of a regular arrangement. And then for the 3rd mark, I'm going to identify its structure. It is a giant metallic lattice or structure, it doesn't matter what you say. Explain why indium is malleable, which means it can be hammered into shape. So you need to say that it is made up of layers of ions which can slide over each other. And remember, these perfect answers are all inside of my revision guide, because the questions really are very similar. Next up, we're going to do a mole calculation. So some of the ammonia from the Haber process is made into fertilizers, such as ammonium nitrate. The equation for the formation of ammonium nitrate is, and a manufacturer makes a batch of 40 kilograms of ammonium nitrate. Calculate the amounts in moles of ammonium nitrate in 40 kilograms of ammonium nitrate. And weirdly, what I would do here is do my table format, but I don't have enough space here. So I'm just going to steal another question and literally write out the equation here. So that's NH3 plus HNO3 forms NH4NO3. So I'm writing out my equation here, and then I'm going to turn it into a table. And remember that mass is mR times number of moles. So this might seem a bit alternative, but I prefer to do it like this. So the question says, find the number of moles of ammonium nitrate in 40 kilograms of ammonium nitrate. So we have 40 kilograms, which I'm going to convert to grams by timesing by 1,000, and I'm after the number of moles, which is X. So we've got 40 kilograms of ammonium nitrate, so I'm writing 40,000 grams under its formula in the mass row, and I've had to times by 1,000 to work out the mass in grams, and I'm looking for the number of moles. So in order to do that, I need to find the MR. So that's going to be nitrogen, which is 14, plus 4 times 1, which is hydrogen, plus 14, plus 3 times 16 to get 80. According to my triangle, number of moles is mass divided by MR, so 40,000 divided by 80, which is 500. So I'm now going to copy that across now, saying that number of moles, with a bit of working so they can see what I've done, is 40,000 divided by 80 equals 500 moles. Next up, deduce the amount in moles of ammonia needed to make this amount of ammonium nitrate. So if I bring my table back, I'm after the number of moles of ammonia, which is here, And the way I do that is to check the mole connection. So I look at the big numbers and they're the same, they're both 1, which is why the number of moles is just 500. And it's easy to see that because it's only worth 1 mark, so we're not expected to do too much here. The next bit of the question asks us to calculate the mass in kilograms of ammonia needed. So bringing my table back, I'm after this number. So mass is MR times number of moles. I've got my number of moles being 500. I need to find my MR of ammonia. So I do 14 plus 3, which is 17. And then lastly, to find the mass, I just do 17 times 500 to get 8,500 grams.